Okay, let's unpack this. Imagine you're organizing a large, complex dinner party, right? And certain guests absolutely cannot be seated next to each other. Maybe, rival politicians or siblings who haven't spoken in
Yes, it's
years.
been there,
Okay.
metaphorically speaking, of course.
Exactly. The constraints are simple to state, but finding a valid seating arrangement for dozens of guests, that becomes incredibly tricky. Or picture yourself as, say, a dedicated delivery driver with hundreds of packages scattered across a sprawling city,
Okay.
needing to find the absolute shortest, most efficient route to deliver every single one before the day ends. I mean, every possible path has to be considered, and the number of paths is just astronomical.
Yeah, it explodes really fast.
Or, if you're an engineer, think about that intricate dance of cramming millions, even billions of tiny transistors onto a microchip the size of your fingernail, making sure none of the delicate wires cross while optimizing for performance in space.
Mm-hmm. Incredibly complex layout problems.
These aren't just frustrating everyday tasks, are they? From a systems thinking perspective, they're deeply interconnected, belonging to a special class of problems that are incredibly easy to describe, but oh boy, fiendishly difficult to solve.
Yeah, the description belies the difficulty.
And at the very heart of computer science lies this question that has captivated and puzzled minds for decades. A question so fundamental it carries $1 million bounty. Are these problems genuinely, fundamentally hard, inherently intractable, or are we just not smart enough yet to find the easy, elegant solution?
That's the crux of it, yeah. The
Yeah.
P versus NP question, essentially.
The answer holds the key to unlocking unimaginable technological potential or confirming the very limits of computation. Well, today, a new formidable player has stepped onto this complex field. This player isn't here to change the rules of the game itself, but to play in ways we never imagined. Artificial intelligence.
Right, AI is starting to tackle these in new ways.
So, as we embark on this deep dive, let's first understand the landscape. We're going to journey through the fundamental classes of computational problems, meticulously delineating what makes them easy or hard.
Okay, the P and NP landscape.
Then we'll shift our gaze to how artificial intelligence, like a powerful new explorer, is boldly reshaping our relationship with this inherent complexity, revealing surprising insights and pushing the very boundaries of what we thought was computationally feasible. Think of it as peeling back layers of a fascinating puzzle.
Revealing not just answers, but maybe even deeper questions along the way.
Exactly.
What's fascinating here is how foundational this topic truly is to everything we do with computers. I mean, at its core, computer science is always asking, what precisely is computable? And maybe even more crucially, what can be computed efficiently?
Right, efficiency is key.
Yeah, and the field of computational complexity theory provides a rigorous formal framework to answer these questions. It classifies problems based on the fundamental resources, primarily time and memory required to solve them using an algorithm.
So it's not just can we solve it, but can we solve it reasonably?
Precisely. This isn't just some abstract academic exercise. It literally shapes the limits of our technology, from, the security of our online banking to the efficiency of global logistics. It informs our understanding of intelligence itself, drawing a sharp boundary between what's practically feasible and what, at least for now, remains computationally infeasible. It's the difference between a task taking milliseconds or, well, eons.
Milliseconds or eons. Okay, let's start with the easier side then, the millisecond side, hopefully. Let's begin our journey by stepping into the world of the easy stuff. Imagine you're trying to sort a shuffled deck of 52 playing cards.
Okay, standard deck.
You know the process. Pick up cards, compare them, put them in order. While it might take you a few minutes, the process is straightforward, predictable, and remarkably efficient. This seemingly simple act is actually a perfect representation of what we call Class P for polynomial time.
P for polynomial. Got it.
It's the bedrock of practical, everyday computation, underlying everything from how your phone organizes your contacts to how your computer processes search queries.
So lots of common tasks fall into P.
Now, the idea of efficient might seem intuitive, but in computer science, it's formalized through a very specific definition. Polynomial time, a concept central to what's known as Cobham's thesis. As many of you familiar with algorithms will know, we often talk about efficiency using big O notation.
Oh yes, big O. Our favorite measure of complexity growth.
An algorithm runs in polynomial time, or O(n) to the power of k, if the number of steps it takes to solve a problem grows gracefully with the size of the input, n in. This means if you double the number of cards you're sorting, the time taken might quadruple in squared, or octuple, O cubed, still manageable, still predictable.
Right, it doesn't explode uncontrollably.
Exactly. This graceful growth is in stark contrast to exponential time, like O2 to the power of n, where doubling the input literally squares the time taken. For instance, if n is 100, 100 cubed is a million operations, which modern computers handle in a blink.
Easy peasy.
But 2 to the power of 100, that's a number with 30 digits. It's a scale of operations completely out of reach for any computer now or in the foreseeable future.
Yeah, that's way beyond astronomical. That's firmly in the eons category.
Cobham's thesis, proposed by Alan Cobham in 1965, posits that this class P corresponds to problems that are efficiently solvable or tractable. It's a widely accepted rule of thumb among computer scientists.
It's a practical definition of feasible.
And while in practice, a theoretical O(n) to the power of 20 polynomial algorithm might actually be less practical than an O2 to the power of n exponential algorithm for extremely small inputs, because those constant factors matter in the real world.
True, the constants can bite you for small n.
This polynomial exponential divide remains the most robust and useful theoretical boundary between what we generally consider feasible and what is intractable. It defines the very limits of what we can hope to compute in a reasonable amount of time.
To really formalize this idea of efficiency, complexity theory leans on an abstract model of computation. Not a physical laptop you can buy, but a conceptual machine. This is Alan Turing's deterministic Turing machine, or DTM.
Ah, the classic Turing machine, the theoretical workhorse.
Exactly. Think of it as the ultimate, perfectly predictable theoretical computer. It has an infinite memory tape, a read-write head, and a finite set of instructions. What makes it deterministic is key. For any given situation, meaning its current internal state and the symbol it's reading, its next step is always uniquely defined.
No choices, no guessing, just follows the rules.
Precisely. There's no randomness, no guessing, no ambiguity involved in its operation. So formally, Class P is defined as the set of all decision problems, those that require a simple yes or no answer that can be solved by a DTM using a polynomial amount of computation time.
Okay, so tied to this theoretical machine, but it still holds.
Yes, and an incredibly important property of Class P is its machine independence. What this means is that if a problem can be solved in polynomial time on any realistic computational model, whether it's a quantum computer of the future or a basic laptop today, it can also be solved in polynomial time on a DTM.
So P is robust. It's not just about Turing machines.
Exactly. This makes P a robust, universal class, not tied to any specific computer architecture or technology. It truly captures the essence of efficiently computable.
Let's bring this abstract definition of P into focus with some concrete examples of problems that live happily within this easy class. We've already touched on sorting, a classic fundamental problem. Algorithms like merge sort or heap sort can sort n items in O(n) log n time, which is highly efficient.
And log n is very good, yeah. Well within P.
Then there's finding the greatest common divisor, or GCD, of two integers. The ancient Euclidean algorithm, discovered over 2 millennia ago, solves this beautifully and efficiently, placing it squarely in P.
Amazing how old some efficient algorithms are.
Right. And in graph theory, the problem of maximum matching, where you find the largest set of non-sharing edges in a graph, also falls into P, with broad applications in everything from scheduling airline crews to assigning students to schools.
Right. Important practical problems solved efficiently.
These aren't just theoretical constructs, they are the workhorses of modern computation.
And this is where the story truly becomes dynamic, because the boundary of the Class P is not static. It's a vibrant frontier of active research that continually expands whenever human ingenuity produces a new algorithmic breakthrough.
So P can grow. Things can move into P.
Absolutely. Consider the problem of linear programming. This involves optimizing a linear objective function, say, maximizing profit, subject to a set of linear inequality constraints, like resource limitations. It's used everywhere.
Economics, logistics, yeah.
Exactly. For decades, the widely used simplex method for linear programming was known to have exponential worst-case performance, meaning it could grind to a halt on certain nasty inputs. It wasn't until 1979 that Leonid Khachiyan, a Russian mathematician, made a pivotal discovery.
Okay, what did he find?
He developed a polynomial time algorithm, known as the ellipsoid method, definitively proving that linear programming is, in fact, in P. This was a monumental shift, opening up new avenues for large-scale optimization.
Wow. So a problem thought potentially hard turned out to be in P.
Exactly. Then think about primality testing. For centuries, Determining whether a given number was prime was a problem whose complexity was completely unknown. While efficient probabilistic tests existed methods that could tell you with a very high probability if a number was prime.
Like Miller-Rabin.
Precisely. But a deterministic polynomial time algorithm, one that could guarantee the answer with certainty in reasonable time, remained elusive. This was a huge open question, fundamental to number theory and, as we'll discuss later, to cryptography.
Right. Primes and crypto are linked.
Very much so. But in a landmark 2002 paper, 3 brilliant Indian computer scientists, Manendra Agrawal, Neeraj Kayal, and Nitin Saxena, presented the AKS primality test. This elegant algorithm finally proved that primality testing is firmly in P.
AKS, I remember that. That was huge news.
It absolutely was. These cases of linear programming and primality testing offer a profound lesson for us. These problems were not born in T. They were admitted into this class of tractable problems only after the discovery of a clever, often highly non-obvious, algorithm.
So the boundary isn't fixed. It depends on our cleverness.
Exactly. This historical evolution is crucial for framing the P versus MP question. It transforms the question from one of simple classification to one about the ultimate limits of algorithmic discovery. Are the problems we currently find difficult simply waiting for their own AKS moment, their own clever algorithmic breakthrough? Or is there a fundamental, uncrossable barrier that forever separates them from the tractable world of P?
Okay, so if that's the easy world of P, where things are efficiently solvable, what happens when we step beyond its neat boundaries? What kind of problems truly stump us, not just in terms of brute force, but fundamentally? This brings us to class NP.
NP, yes. The realm of efficient verification.
Right. A much larger and more enigmatic class of problems. We may not know how to find solutions to these problems efficiently, but they share this tantalizing property. Their solutions are easy to check. Think back to our dinner party seating chart.
Okay, the dreaded seating chart again.
You might spend days agonizing over the perfect arrangement, trying out combinations, but if I simply hand you a proposed chart, you can verify in minutes whether it breaks any of your no-sit-together rules.
Yeah, checking is quick. Just look at the neighbors.
The creative, often frustrating search for a solution seems worlds away from the simple, mechanical act of checking one. And that, in a nutshell, defines NP.
That's a perfect way to put it. The abbreviation NP itself stands for non-deterministic polynomial time. This comes from its first formal definition, which is based on a theoretical model called a non-deterministic Turing machine, or NTM.
Okay, NTM, so related to the DTM, but non-deterministic. How?
Unlike its deterministic counterpart, an NTM can sort of guess which paths to take at each step. It's like it has magical foresight, or can explore multiple paths simultaneously. So for a problem like the traveling salesman problem, an NTM could theoretically guess a permutation of cities, essentially magically pick the right tour.
Like a lucky guess.
Kind of. And then, in a deterministic phase, check its total length in polynomial time. If at least one such guess leads to a solution, the problem is considered to be an NP. It's a way of modeling that leap of intuition, or maybe just a brute force search where one path happens to work.
Okay. That's a bit abstract. Is there another way to think about it?
Yes, absolutely. And arguably a more intuitive and practically useful definition of NP is based on the concept of a polynomial time verifier. A problem is an NP if, for any yes instance, there exists a certificate or a piece of evidence that can be used to prove the answer is yes.
A certificate, like a proof.
Exactly, like a proof or a proposed solution. Crucially, this certificate must be verifiable for correctness by a deterministic Turing machine, our perfectly predictable computer in polynomial time. This verify-don't-solve paradigm is key to understanding NP's significance.
So find me the solution, hard, or give me a potential solution and I'll check it, easy.
Precisely. These two definitions, one based on a non-deterministic solver and the other on a deterministic verifier, are formally equivalent, highlighting the core idea of problems where solutions are hard to find but strikingly easy to check.
The concept of a certificate is really central to this verifier-based definition of NP, isn't it? It's that piece of magic information that makes verification easy, almost like a secret key.
It is. It's the witness that proves the yes answer.
Let's make this more concrete. Take the decision version of integer factorization. Given two integers, n and m, doesn't have a factor f such that f is greater than 1 but less than f. If the answer is yes, the certificate is simply the factor f itself. A verifier can quickly check the certificate by performing a single division. n divided by f, to see if there's a remainder. That verification is a simple polynomial time operation.
Right. Division is fast. Finding f, though, that's thought to be hard for large n.
Exactly. Or consider the decision version of the traveling salesman problem, or TSP. Given a set of cities and the distances between them, is there a tour that visits every city exactly once with a total length less than k?
It's a classic TSP decision problem.
The certificate here is the specific sequence of cities forming the proposed tour, like city A to city C to city B to city D and back to city A. The verifier's job is straightforward.
Yeah.
Sum the distances along that proposed path and check if the total is indeed less than k.
Simple addition and comparison. Definitely polynomial time.
This is simple addition and comparison, easily done in polynomial time. The monumental difficulty lies not in checking a given tour, but in finding that short tour among the astronomical factorial number of possibilities that grow unbelievably fast, even for a relatively small number of cities.
Factorial growth is even worse than exponential, really. It's brutal.
And then there's Boolean satisfiability, or SA. Given a Boolean logic formula, for example, something like A or B and D, not B or C, is there an assignment of true-false values to its variables, A, B, C, that makes the entire formula evaluate to true?
The granddaddy of NP problems, SAT.
The certificate is the assignment itself, say A true, B false, C true. The verifier simply substitutes these values into the formula and evaluates it, which is a fast mechanical process.
Plug and chug. Easy to check.
You see the pattern now, right? The certificate acts as the critical piece of evidence that transforms an incredibly difficult search problem into a simple verification task. It's the difference between finding a needle in a haystack and confirming a needle is indeed the one you were given.
Yeah, that's a great analogy. And if we connect this to the bigger picture, this potential gap between finding a solution and checking one mirrors a deep truth about many creative and scientific endeavors, and indeed, about the human experience of problem solving.
How so?
Discovering a brilliant solution, whether it's a groundbreaking mathematical proof, an elegant engineering design, or a revolutionary scientific theory, can be arduous, seemingly intractable, requiring flashes of insight, leaps of intuition, and a painstaking search through a vast space of possibilities. Think of, the solitary genius working for years on a theorem.
Right, the eureka moment doesn't come easy.
Exactly. However, once the final product is presented, say a completed proof or a detailed blueprint, it can often be evaluated and validated by others through a methodical step-by-step process that is far less complex, far less creative than the initial act of creation.
Okay, I see the parallel. Verification is often procedural.
Right. The NP class formalizes this fundamental difference between discovery and appraisal. The P versus NP question, therefore, asks whether this perceived gap is a fundamental feature of reality, an inherent speed limit to discovery, or merely a consequence of our current ignorance or lack of sufficient computational power.
So, is creativity inherently harder than checking?
That's the deep question. If P were equal to NP, it would imply that the creative leap required to find a solution is, computationally, no more difficult than the methodical process of verifying it. This isn't just about faster calculations. It challenges our very understanding of intuition, creativity, and the unique spark of human intellect.
Wow.
Would we still revere the solitary mathematician toiling for decades? Or would our intellectual landscape be dominated by AI systems churning out provably correct theories on demand? This is where the mathematical question transcends technology and becomes a deep philosophical inquiry into what it means to be intelligent and to create.
And this, I think, is where the narrative truly escalates. It leads us right to the precipice of what many consider the single most profound, open question in computer science and mathematics, the P versus NP problem.
The million-dollar question itself.
It's a mystery that holds $1 million bounty and has baffled the brightest minds for decades. And it's crucial to clarify a common point of confusion here. P versus NP is not about a new class of problems called PNP. Rather, it's the fundamental question of whether the two classes, P and NP, are in fact one and the same.
Are they the same set of problems, or is P strictly smaller?
Right.
That's it.
Formally, we know that P is a subset of NP, meaning that every problem that can be solved quickly can certainly have its solution checked quickly. If you can find a short tour for the traveling salesman, you can certainly check that it's short.
P is definitely inside NP. That's the easy part.
The $1 million open question is whether this inclusion is proper, meaning P is strictly smaller than NP, implying there are problems in NP that are inherently harder to solve than to check, or if the two classes are identical, meaning P and P.
Does NP contain problems not in P? Or is everything in NP actually also in P, if we're just clever enough?
In other words, does every problem whose solution can be verified in polynomial time also have an algorithm that can find that solution in polynomial time? This is the core enigma.
Yep.
This question was first formally articulated in its modern form by Stephen Cook in his seminal 1971 paper, The Complexity of Theorem-Proving Procedures. Its profound importance was recognized globally by the Clay Mathematics Institute, which in 2000 designated it as one of the 7 Millennium Prize problems, offering a $1 million reward for the first correct proof.
$1 million, and eternal fame in the math and CS worlds. No small prize.
While the question remains officially unresolved, the overwhelming consensus among theoretical computer scientists is that P does not equal NP. This belief stems from decades of fruitless searching. Despite the immense incentives and countless brilliant attempts, no one has ever found a polynomial time algorithm for any of the thousands of known hardest NP problems.
Yeah, the lack of progress is pretty strong circumstantial evidence, you could say. It feels like if there was an easy solution, someone would have stumbled upon it by now, given how many smart people have looked.
It's a testament to the perceived intractability of these problems.
Exactly. When I first grappled with the P versus NP problem, it felt like my brain was trying to hold two contradictory ideas at once.
Yeah.
The traveling salesman problem. That's like looking at a single, incredibly daunting mountain peak. You're trying to figure out the best way to conquer that specific challenge.
Right, focused on one hard problem.
But the P versus NP problem, it's not about one peak at all. It's asking about the very nature of the entire mountain range of hard problems. Is there a secret, universally applicable, easy path, maybe a hidden tunnel or a magic elevator that works for every single peak in this vast, rugged landscape?
Okay. It's about the whole class, not just one instance.
Exactly. It's a question at a much higher level of abstraction, seeking a universal law. And that's precisely why it's captivated so many brilliant minds. The other Millennium problems, concerning everything from the distribution of prime numbers to the fundamental nature of space itself, share this quality of seeking deep, universal truths, placing them at the highest peaks of human inquiry.
From a systems thinking lens, computer scientists in the 1970s made a stunning breakthrough that fundamentally changed how we categorize these challenges. They identified a subset of NP problems, called NP-complete, that are the hardest of them all.
NP-complete. The pinnacle of NP hardness.
These problems are like the ultimate boss level in a video game, or perhaps better, a set of master keys that can unlock any door in a vast complex. What's truly mind-boggling is that they are all reducible to one another. This is a form of isomorphism, a shared underlying structure that means solving one efficiently would effectively solve them all.
Right, they're computationally equivalent in a profound way.
To define this more formally, we use the technique of polynomial time reduction. A problem A is reducible to a problem B if any instance of A can be transformed into an instance of B in polynomial time, such that the answer to B's instance is yes, if and only if the answer to A's instance is yes.
Okay, so it's like translating problem A into problem B quickly.
Essentially, yes. This means that if you had a fast algorithm to solve B, you could use it to solve A quickly too, by just transforming A into B and then solving B. So effectively, problem B is at least as hard as problem A.
Because solving B lets you solve A. Makes sense.
This concept gives rise to two crucial definitions that are often confused but are distinct. First, an NP-hard problem is one to which every problem in the class NP can be reduced in polynomial time.
NP-hard. So at least as hard as anything in NP.
These are the titans of complexity. They are at least as hard as any problem in NP, though an NP-hard problem doesn't necessarily have to be an NP itself. For example, the halting problem, which asks if a given program will ever stop, is NP-hard, but it's not even decidable by a computer, let alone an NP.
Right, the halting problem is super hard, way beyond NP.
The optimization version of the traveling salesman problem, find the absolute shortest tour, is also NP-hard because it asks for the best solution, not just a yes-no answer about whether a tour under length K exists.
Optimization versus decision. Got it.
Second, an NP-complete problem, or NPC, is a problem that satisfies two very specific conditions. It's in the class NP, meaning its yes solutions can be verified in polynomial time.
Condition 1. Verifiable quickly.
And it's NP-hard, meaning every other problem in NP can be reduced to it.
Condition 2. Everything else in NP reduces to it.
So NP-complete problems are, by definition, the hardest problems in NP. They sit at the very pinnacle of computational difficulty within the NP class.
The kings of the NP mountain range, so to speak.
Exactly.
And this leads to the staggering implication that underscores the importance of the P versus NP question. If a polynomial time algorithm could be found for any single NP-complete problem, just one.
Just one. Like SAT or TSP.
Any single one. Then, by the power of polynomial time reductions, every problem in NP could be solved in polynomial time. This would mean that P and PP. The entire class NP would dramatically collapse to P, meaning that suddenly all those problems we considered intractable would become efficiently solvable.
The whole house of cards comes down.
It would be like discovering a single Rosetta Stone that instantly translates every intractable puzzle into a simple, solvable one. The consequences would be nothing short of world-altering, truly reshaping the very fabric of our technological civilization.
It's almost dizzying to contemplate the domino effect, isn't it? Such a discovery wouldn't just be an academic triumph, it would ripple through the very foundations of our technological civilization.
Oh yeah, fundamentally.
Let's really drill down into what that would mean for something as fundamental as cryptography and our digital security. The entire edifice of modern public key cryptography, which secures online banking, e-commerce, all our private communications, relies on the assumption that certain problems are computationally hard specifically. NP problems are those closely related to them.
Like factoring large numbers for RSA.
Exactly. Systems like RSA depend on the inherent difficulty of factoring very large numbers. If PMP, an efficient algorithm for factoring, would instantly exist, and these cryptographic systems would become instantly obsolete, all encrypted data could be broken with relative ease.
Everything. Bank accounts, government secrets, private messages, all gone.
Leading to a catastrophic and unprecedented collapse of digital security worldwide. Imagine the chaos.
It's almost unimaginable. Total digital meltdown.
Then there's the vast realm of optimization, logistics, and economics. Many of the most challenging optimization problems faced by industries and scientists every day are NP hard. This includes the traveling salesman problem for routing delivery trucks, the knapsack problem for efficient resource allocation,
Circuit layout, protein folding. The list goes on.
and the incredibly complex task of circuit layout optimization for designing the next generation of microchips. In a PNP world, we could find perfectly optimal solutions to these problems efficiently, not just good enough ones.
Perfect optimization for everything.
This would enable perfectly optimized airline schedules that eliminate delays, global supply chains with minimal waste, hyper-efficient energy grids, and microchip designs that are leaps and bounds beyond every sector.
A true technological utopia in some ways. Assuming we survive the crypto collapse first.
Good point. And in the burgeoning fields of artificial intelligence and machine learning, the training of many sophisticated models, especially deep neural networks, involves solving NP-hard optimization problems to find the best set of parameters. If PNP, we could efficiently find the provably optimal parameters for these models,
Perfect machine learning, instantly.
leading to a dramatic, almost unimaginable leap in AI capabilities, accuracy, and reliability. Imagine AI that could consistently find the absolute best way to learn, rather than relying on educated guesses and approximations.
The singularity might arrive a lot faster than expected.
And in biology and medicine, the protein folding problem, which seeks to determine the precise three-dimensional structure of a protein from its amino acid sequence, is known to be NP-hard. An efficient solution to this would revolutionize drug discovery,
Designing drugs and biomaterials from scratch, curing diseases.
allowing scientists to design novel proteins and enzymes from scratch, leading to revolutionary new drugs, therapies, and biomaterials that are currently beyond our grasp.
The potential benefits are just staggering.
But perhaps most profoundly, a proof of PMP wouldn't just automate discovery, it would fundamentally redefine it. Imagine the profound aha moments that define breakthroughs in mathematics, moments of seemingly inexplicable human genius suddenly becoming reducible to a mechanical search.
Right. Formal proofs are easily verifiable in polynomial time. They are, by definition, in NP.
Therefore, if PNP, a computer could theoretically find a proof for any theorem that has a proof of a reasonable length. This isn't just about faster calculations, it challenges our very understanding of intuition, creativity, and the unique spark of human intellect.
Yeah, would mathematical creativity just become computation?
Would we still revere the solitary mathematician toiling for decades? Or would our intellectual landscape be dominated by AI systems churning out provably correct theories on demand? This is where the mathematical question transcends technology and becomes a deep philosophical inquiry into what it means to be intelligent and to create.
So that's the PNP world. What about the flip side? What if, as most suspect, P does not equal NP?
Right, what if the consensus is correct?
A proof that P does not equal NP, while perhaps less dramatic in its immediate impact, would be equally significant and, in a way, just as profound. It would formally confirm what is currently the working assumption of most of the scientific and technological world.
So, confirming the status quo but with mathematical certainty.
Exactly. It would provide a definitive mathematical proof that certain problems are inherently intractable, that their difficulty isn't just a limit of our current ingenuity, but a fundamental property of the universe. It would mean that for problems like the traveling salesman problem or Boolean satisfiability, no amount of cleverness or future computational power will ever yield a general, efficient algorithm that finds the exact solution in all cases.
A universal speed limit.
The universe would, in essence, have a built-in speed limit for solving certain kinds of problems. An irreducible computational barrier. Furthermore, such a proof would provide immense justification and validation for the enormous body of research dedicated to developing heuristics and approximation algorithms.
So the good enough approaches become provably necessary.
Yes. These methods, which aim for good enough solutions rather than perfect ones, would be formally cemented as a necessary and permanent part of our computational toolkit, not just a temporary stopgap until a better algorithm is found. This would mean focusing research where it is most effective, on tailored approximate solutions.
Makes sense. Focus on what's possible.
And finally, the foundations of modern cryptography would be placed on much firmer theoretical ground. It would confirm that the security of our digital lives is based on a genuine, provable computational hardness, not just our current inability to find the clever shortcut. This would be a relief to cybersecurity experts worldwide.
Okay, so PNP secures our secrets and validates a lot of current practice. Now, for this incredible theory of NP completeness to be useful, for it to be anything more than an abstract curiosity, at least one NP complete problem had to be shown to exist, right? Someone had to find that first hardest problem.
Absolutely, you need an anchor point.
This was the monumental achievement of the Cook-Levin theorem, independently proven by Stephen Cook in his 1971 paper and Leonid Levin in his 1973 work. It was a true breakthrough that solidified the entire field.
Cook and Levin, foundational names.
The Cook-Levin theorem states that the Boolean satisfiability problem, or SAT, is NP-complete. SAT, remember, is the problem of determining if there exists an assignment of truth values, true or false, to the variables in a given Boolean formula that makes the entire formula evaluate to true.
The first domino to fall, proving SAT was NPC.
The ingenious proof of the Cook-Levin theorem is a truly profound piece of work. It essentially acts as a universal translator, or a Rosetta Stone, for the entire NP class. Here's the core idea. Cook and Levin proved that you can take any problem in MPP, let's say our traveling salesman problem, or the dinner party seating, or even verifying a mathematical proof.
Any problem where solutions are easy to check.
And automatically and efficiently transform it into an instance of the Boolean satisfiability problem, or SAT.
Wow. Yeah.
Imagine writing down all the steps a hypothetical non-deterministic computer would take to solve your NP problem, including all its guesses and checks. The theorem shows you can encode this entire computation into one gigantic but cleverly structured SAT formula.
Encode the computation itself as a logic puzzle. That's brilliant.
And here's the kicker. That SAT formula will be satisfiable, meaning you can find a true-false assignment that makes it true, if and only if your original NP problem had a yes answer.
So solving the SAT formula is equivalent to solving the original NP problem.
Exactly. This means if you had a fast way to solve SAT, you'd immediately have a fast way to solve every other problem in NP. That's why SAT became the very first foundational NP-complete problem, the anchor for the entire class of hardest problems, a true fulcrum for the theory.
You know, the Cook-Levin theorem, it really felt like it just blew the doors open. Once SAT was established as NP-complete, researchers no longer needed to perform the complex, intricate Turing machine encoding for every new problem they suspected was hard.
Right. They could just reduce from SAT instead. Much easier.
Exactly. Instead, they could simply show a polynomial time reduction from SAT or another problem already known to be NP-complete to a new problem. This created a powerful domino effect, rapidly expanding the known universe of NP-complete problems.
Like falling dominoes, proving one proves others.
In 1972, Richard Karp did exactly this in a landmark paper titled Reducibility Among Combinatorial Problems. He demonstrated that 21 other famous and practically important problems were also NP-complete by showing how each of them could be reduced to SAT or to another problem on his list.
Karp's 21 problems, that's legendary.
It really is. This comprehensive list included problems from diverse areas like graph theory, logic, and optimization. For example, he showed that the clique problem, finding a complete subgraph of a given size within a larger graph, is NP-complete.
Finding a tight-knit group in a network.
So is the vertex cover problem, identifying the smallest set of vertices that touch every edge in a graph. And the Hamiltonian cycle problem, which asks if a graph contains a simple cycle that visits every vertex exactly once, a close cousin to the traveling salesman problem, also landed on the list, as did 3SAT, a restricted but still incredibly hard version of SAT.
So many core problems turned out to be equivalent in difficulty.
Karp's work was transformative. It demonstrated that NP-completeness was not an isolated theoretical curiosity, but a pervasive and fundamental property shared by a vast, intricate web of seemingly unrelated problems. It showed that finding an efficient algorithm for scheduling factory jobs, designing a complex circuit board, or finding a specific pattern in a vast network were all, at their core, computationally equivalent.
That's a powerful unifying concept.
It is. This insight is immensely powerful for engineers and researchers. It provides a formal tool to recognize when a new problem is likely intractable. If one can reduce a known NP-complete problem to it, then searching for a perfect, efficient algorithm is likely a fool's errand.
Saves wasted effort.
Exactly. It channels research efforts towards the most promising avenues, developing effective approximation algorithms, clever heuristics, or focusing on finding exact solutions only for special, constrained cases of the problem. It's like a warning sign that says, beyond here, be prepared for exponential complexity.
Okay, so that sets the stage. We have P, easy, NP, easy to check, hard to solve, and NP complete, the hardest and NP all equivalent. Now, enter AI. For 50 years, we've largely treated these NP-complete problems as a fundamental barrier, a computational Everest. We've designed clever workarounds and developed good enough heuristics because we assume perfection is simply unattainable within reasonable timeframes.
That's been the standard approach, yeah, coping with hardness.
But now, as William L. Weaver discusses in AI That's Learning to Play, artificial intelligence is attacking this barrier not with a single battering ram, but with a multi-pronged assault that is fundamentally reshaping our relationship with complexity.
Right. AI isn't necessarily trying to prove PNP, but is finding new ways to deal with NP hard problems and even optimize P problems.
And AI is leveraging the power of machine learning and reinforcement learning to attack these intractable problems in novel ways, and this assault is proceeding on 3 distinct fronts.
The first, and perhaps the most immediately practical role, is AI as the master apprentice, or what we could call the heuristic architect.
Heuristic architect, I like that. Building better shortcuts.
Exactly. The brutal practical reality is that the real world cannot wait for miraculous, perfect algorithms for NP hard problems. For a problem like the traveling salesman problem, a brute force approach that checks every possible tour is computationally impossible for anything beyond a handful of cities.
We established that, yeah. Factorial explosion.
So classical heuristics, like the nearest neighbor algorithm, where you simply go to the closest unvisited city next, offer a simple, fast alternative. They aim to find a reasonably short tour, a good enough solution, but without the guarantee of finding the absolute optimal one.
Better than nothing, but maybe not great.
For many NP hard problems, this is the reality we live with. We trade the guarantee of optimality for the feasibility of getting an answer at all. This is precisely where a new and vibrant field called machine learning for combinatorial optimization, or ML4CO, comes in.
ML4CO. Okay, so applying machine learning here.
It seeks to automate and significantly improve this process of heuristic design. The core idea is that many real-world applications involve solving instances of the same problem repeatedly, often drawn from a specific data distribution.
Like that delivery company's daily routes.
Precisely. A major logistics company solves a new vehicle routing problem every single day, perhaps hundreds of times a day, but the geographical locations of warehouses, the traffic patterns, and the typical customer locations are frequently similar. ML4CO aims to leverage this vast historical data, treating it as experience, to learn a specialized heuristic that outperforms generic hand-tuned ones for that specific context.
So the AI learns from past routes to make better future routes.
Essentially, yes. Instead of a human engineer spending months fine-tuning a heuristic, an AI can learn it from the data.
How does it learn? What are the techniques?
This is achieved through a variety of cutting-edge machine learning techniques. We're seeing powerful applications of supervised and deep learning, particularly with graph neural networks, GNNs.
GNNs, right. Good for network-like problems.
Incredibly adept at understanding complex relationships within data structured like networks, perfect for representing problems like TSP or circuit design. These GNNs can be trained on large sets of problem instances where optimal solutions are known, or at least very high-quality approximate solutions have been found. The GNN then learns to recognize intricate patterns in the problem structure and predict properties of a good solution, guiding a search process.
So it learns what good solutions look like.
Kind of. And reinforcement learning, or RL, has become a particularly popular approach, where an RL agent constructs a solution step by step, treating the problem as a sequential decision task, much like playing a game.
Ah, RL again, like learning to play the build-a-solution game.
Exactly. We also see fascinating hybrid approaches, combining ML and traditional solvers. For instance, a machine learning model might quickly prune a vast search space, identifying a promising region of solutions which is then handed off to a classical, exact solver for final refinement, combining the best of both worlds.
That's fascinating. So digging deeper into reinforcement learning in the solution space, it provides a really intuitive framework for tackling these notoriously challenging combinatorial optimization problems. The process of building a solution, like adding cities to a tour one by one in TSP, can be modeled as an RL agent moving through a series of states in an environment, much like a robot learning to navigate a maze.
Yeah, the game analogy works well here.
Let's go back to the traveling salesman problem to illustrate. An RL agent can be designed like this. Its state at any given moment is the partial tour it has constructed so far, the set of visited cities, and the last city it arrived at.
Okay, where am I now and where have I been?
Its action is to select the next unvisited city to add to the tour, essentially making a decision at each step.
Which city next?
And the reward. The agent receives a reward after completing a full tour, and that reward is typically inversely proportional to the tour's total length. So shorter tours yield higher rewards, effectively telling the agent, good job, you found a more efficient path.
Learned by trial and error, guided by the final score.
Through countless trials and errors over millions of episodes, the agent learns a policy, which is essentially a refined strategy for consistently choosing the next city from any given state. The ultimate goal is for it to learn a policy that reliably produces short, near-optimal tours for a wide range of instances.
It learns its own heuristic, basically.
Exactly. This approach effectively learns a sophisticated heuristic for constructing TSP solutions. Related meta-heuristics, like ant colony optimization, where simulated ants lay down digital pheromone trails to communicate good paths.
Yeah, inspired by nature.
And genetic algorithms, which evolve a population of candidate tours through selection, crossover, and mutation, all operate on similar principles of guided iterative search. AI-driven systems using these techniques can provide remarkably near-optimal results for large-scale TSP instances, much more efficiently than exact methods, making problems feasible that were once considered impossibly complex.
Now, with all this talk of AI's burgeoning capabilities in ML4CO, it's fair to ask, are we on the cusp of AI replacing all our classical algorithms? Or is there a more nuanced reality?
Yeah. Is this the end of traditional algorithm design?
It's crucial, I think, to maintain a critical perspective here. While the field of machine learning for combinatorial optimization is undeniably maturing and showing immense promise, recent comprehensive benchmarks offer a sobering counterpoint. For certain notoriously difficult problems, like the maximum independent set problem, where you're trying to find the largest group of vertices in a network where no two are directly connected.
Another classic hard graph problem.
Even the leading AI-inspired methods are still consistently outperformed by highly optimized classical solvers, such as Kami's. This tells us AI isn't a silver bullet yet.
Okay. So the old ways aren't dead yet.
Not by a long shot. Some studies have even questioned whether the graph neural networks in certain popular ML4CO models are learning truly meaningful representations at all, suggesting that sometimes they can be replaced by random values without a significant drop in performance.
Really? Random values work almost as well. That's surprising.
It implies that maybe the clever algorithmic framework around the GNN is doing most of the heavy lifting, rather than the GNN itself learning profound insights into graph structure. This indicates that while promising, ML4CO is not yet a universal replacement for decades of specialized algorithmic research.
So more hype than substance in some cases.
Perhaps potential not yet full realized is fairer. The promise of ML4CO is not necessarily to find a single, universally optimal algorithm for all problems, but rather to create a new class of powerful, specialized solvers that can be trained and continually improved for the specific types of hard problems an organization faces, learning from experience to get better over time. It's about building adaptable, bespoke problem solvers.
Okay, adaptable heuristics, that makes sense. Now, what about the second front? You mentioned AI as an alien genius.
Ah, yes, the algorithm discover. This is fascinating stuff.
In a fascinating twist, as William L. Weaver notes, Google's AlphaDev project turned AI loose on the easy P problems, like sorting.
Right, not NP hard stuff, but fundamental P problems.
This is where AI truly acts as the alien genius, the algorithm discoverer. Instead of just finding good enough solutions for hard problems, AlphaDev aimed to discover fundamentally new, provably correct, and more efficient algorithms for problems that were already well understood and considered easy problems that human experts had already optimized for decades.
Trying to beat humans at their own game, on problems we thought we'd mastered.
This isn't just about small tweaks, it's about discovering new ways to think about fundamental operations. The core conceptual breakthrough of AlphaDev was to reimagine algorithm discovery itself as a game that a reinforcement learning agent could be trained to play and win.
Algorithm discovery as a game, okay.
Instead of learning to master a board game like Go or chess, the AlphaDev agent learns to master the game of writing a computer program. The objective is to construct, one instruction at a time, an algorithm that is both perfectly correct and faster than any existing human-designed benchmark.
Building code instruction by instruction, aiming for speed and correctness.
This approach starts from a blank slate, exploring the fundamental building blocks of computation without human preconceptions about what an algorithm should look like. AlphaDev's search space is the vast, complex world of low-level assembly instructions, the primitive operations the computer CPU directly executes. This is where the true granular efficiency is found.
Down in the weeds of assembly code, that's hardcore optimization. AlphaDev is built upon the architecture of AlphaZero, DeepMind's celebrated game-playing AI that famously conquered Go, chess, and shogi. In this novel assembly game, the state at any point is a sophisticated combination of two things: the algorithm, or sequence of assembly instructions generated so far, and the resulting state of the CPU's registers and memory after executing that partial algorithm on a carefully selected set of test inputs.
So it knows the code it's written and what that code does.
Exactly. A powerful transformer network, well-suited for understanding the intricate dependencies in sequential data, is used to encode the program itself, allowing the AI to read and comprehend its own evolving code. An action consists of choosing a legal assembly instruction to append to the end of the current program.
Picking the next line of code.
To make the enormous search space of possible programs tractable, the set of possible actions is constrained by a set of carefully engineered rules. For example, ensuring memory locations are accessed safely and registers are used correctly. The reward is the crucial element that guides the agent's learning, a sophisticated function combining two signals, a score for correctness and a score for latency, or speed.
Rewarded for working right and working fast.
Precisely. The agent is heavily rewarded for producing an algorithm that correctly performs the desired task, such as sorting a list, and is proportionally penalized for being slow. The ultimate win condition is discovering an algorithm that is both 100% correct and demonstrably faster than the state-of-the-art human benchmark.
How does it search this huge space?
To navigate the astronomical number of possible programs and instruction sequences, AlphaDev employs a Monte Carlo tree search, guided by a deep neural network that predicts which actions or instructions are most promising from a given state and what the long-term reward is likely to be. It's essentially learning to anticipate the efficiency gains of different coding choices.
Wow. So it plays the coding game using techniques from board games. And the tangible breakthroughs from AlphaDev are genuinely impressive, having yielded concrete, real-world results that have actually been vetted and deployed in production systems that affect millions of users daily.
It wasn't just theoretical then.
No. For sorting algorithms, AlphaDev's primary achievement was discovering new sorting routines. For short sequences of 3 to 5 elements, these are incredibly common operations called billions of times a second. It found algorithms that were up to a staggering 70% faster than the highly optimized human-developed versions that have been in use for decades.
70% faster on short sorts. That's huge.
For larger sequences of over 250,000 elements, the improvement was a more modest but still significant 1.7%. While that might sound like a small percentage, These sorting routines are among the most fundamental and frequently executed pieces of code in all of computing,
Yes, sorting is everywhere. Database indexes, graphics.
underpinning everything from database queries to graphics rendering. Even tiny constant factor speedups at this level cascade into massive global computational savings. After independent verification and rigorous testing, these new AI-discovered algorithms were integrated into the LLVM libx++ standard library, a core component used to compile C++ code for millions of applications worldwide.
So it's actually in the C++ library now. That's amazing.
This was the first change to this part of the library in over a decade, and the very first time an algorithm discovered by reinforcement learning was ever added.
History being made by AI code.
What's even more remarkable is the sheer novelty of these discoveries. AlphaDev didn't just make incremental improvements, it discovered fundamentally new and counterintuitive instruction patterns that human experts, despite decades of meticulous optimization, had simply missed.
Like what? Any examples?
For example, it came up with something nicknamed the AlphaDev swap and copy move, which cleverly saves an instruction by connecting items in a way that appears on the surface to be a logical error, but is in fact a perfectly correct and more efficient shortcut.
Huh. A move that looks wrong, but works better. That is alien.
This is eerily reminiscent of DeepMind's AlphaGo's famous Move 37, an unexpected creative move in the game of Go that defied conventional wisdom and was absolutely key to defeating a world champion. It suggests as an alien creativity, a way of reasoning about computation that is fundamentally different from how humans approach it.
Finding loopholes or efficiencies we're blind to.
AlphaDev also discovered new hashing algorithms that were up to 30% faster for certain input sizes, which have since been integrated into Google's open-source Absol C+ library, further demonstrating its practical impact.
Faster hashing too. Okay, so real practical speedups on P problems. This raises an important question. What does AlphaDev's success truly mean for the P versus NP problem?
Right. Does beating sorting mean AI can crack NP?
It's crucial to understand the scope and limits of these achievements. Sorting is a problem that is firmly and definitively in the class P. The best comparison-based sorting algorithms have a time complexity of O(n) log n. AlphaDev did not change this fundamental complexity.
Still n log n, fundamentally.
It did not discover an O(n) sorting algorithm, which would be a theoretical impossibility for comparison-based sorting. Instead, what AlphaDev achieved was making the practical implementation of a known P-class algorithm more efficient at the lowest level of computation. It reduced the constant factors in its real-world running time.
It optimized the code, not the underlying complexity class.
Exactly. It found a faster program, an optimized piece of code, not a fundamentally new complexity class for the problem. So in a way, the sheer difficulty of AlphaDev's achievement paradoxically reinforces the perceived difficulty of P versus NP.
How does making sorting faster make P versus NP seem harder?
Think about it. DeepMind deployed a state-of-the-art AI system with immense computational resources and an army of engineers to wring out these constant factor speedups, saving just a few assembly instructions from a well-understood polynomial time problem. The effort required was monumental.
Just for a small speed up on an easy problem.
A testament to how optimized these easy problems already are. To believe that a similar AI could tackle an NP-complete problem and find a polynomial time solution would require a leap of faith many, many orders of magnitude greater. Such a feat would not involve saving a few instructions, but rather discovering a completely new mathematical structure that fundamentally transforms the problem's complexity from exponential, like O2 to the power of n, to polynomial, like On to the power of k.
A totally different kind of breakthrough required.
The immense challenge of optimizing within P makes the chasm between P and NP appear even wider and more fundamental, suggesting the barrier between them is not just one of degree, but of kind.
Okay, that's a really important clarification. AlphaDev is amazing engineering, but it doesn't collapse the hierarchy. That brings us to the final frontier, the most speculative one in our journey. The quest for mathematical proof.
AI as mathematician, or at least a helper.
If the P versus NP problem is ever to be resolved, it will require a rigorous, formal mathematical proof that is checkable by the global community of mathematicians. While AI is far from autonomously producing such a proof today, it is rapidly becoming a powerful assistant in the domain of automated theorem proving, or ATP.
ATP, using computers to prove things.
The field dedicated to using computers to construct and verify mathematical proofs with absolute logical certainty. ATP systems use formal logic, a set of axioms assumed to be true, and an inference engine that applies logical rules to derive new true statements, step by precise step.
Building proofs logically, block by block.
ATP has already achieved remarkable, if often behind-the-scenes, practical success. One major area is formal verification, where it's used to rigorously prove the correctness of mission-critical systems. Remember the infamous Intel Pentium FDIV bug in the 1990s?
Oh yeah, the floating point bug cost them a fortune.
A tiny flaw in the floating point division unit cost Intel hundreds of millions of dollars and severely impacted public trust in computing. This incident was a massive wake-up call for the industry, spurring enormous investment in formal methods. Today, ATP systems are routinely employed by companies like Intel and AMD to formally verify their microprocessors.
Checking the chip designs mathematically before they're built.
Meticulously checking billions of potential computational paths to ensure there are no hidden flaws before chips are ever manufactured and shipped. Similarly, in fields like aerospace, automotive, and medical devices, ATP helps prove the safety and reliability of complex software that controls everything, from autopilot systems to patient monitoring equipment.
Proving safety-critical software is correct. It's huge.
Providing a level of mathematical certainty that manual testing simply cannot achieve. This is where the abstract world of logic directly impacts the reliability of our most crucial technologies.
Historically, formal methods have been incredibly powerful but also extraordinarily laborious, often requiring expert human guidance and an immense amount of time. The recent convergence of AI and formal methods is creating a new generation of tools that aim to combine the speed and pattern recognition abilities of machine learning with the rigorous precision of logical deduction.
AI making formal methods easier to use.
That's the hope. This is fundamentally transforming how we approach formal reasoning, making it more accessible and scalable. On one hand, we're seeing AI for formal methods. Generative AI, especially large language models or LLMs, is being explored as a way to make formal methods more accessible and efficient.
Using LLMs to write formal specs.
For instance, an engineer could describe a system's desired properties in natural language, and an LLM could generate a first draft of a formal specification in a specialized formal language. This draft can then be refined through an iterative workflow often called genification, where a sophisticated model checker automatically tests the specification for correctness and consistency.
The checker finds flaws.
If it finds a flaw, that flaw is precisely identified and fed back to the LLM, which then attempts to correct and refine the specification. This iterative loop combines AI's generative speed and intuition with the exhaustive, precise checking of formal verification.
Interesting. And the other way around, ML helping ATP.
Conversely, machine learning is being used to make ATP systems themselves far more powerful. The search for a proof can be seen as navigating an enormous branching tree of possible logical deductions. ML models, including deep learning and reinforcement learning, are being trained to guide this search more intelligently and efficiently.
Using RL to guide the proof search, like AlphaDev finding code.
Exactly like that. RL agents, modeled on the AlphaZero architecture, can be trained to play the game of theorem proving, where the state is the current set of proven statements and the action is the application of a logical rule or axiom. The agent learns a policy to select the most promising steps, dramatically pruning the vast search space and significantly increasing the chances of finding a proof that might otherwise take human mathematicians years or even centuries. This is an exciting frontier where AI is learning to think like a mathematician, albeit in a very structured way.
So the ultimate speculative question, the one that truly fires the imagination, could an AI actually solve the P versus NP problem?
The billion-dollar question again, but for AI this time.
The current consensus among leading computer scientists and mathematicians is no, not directly, at least not with the AI we have today. LLMs and other deep learning models are fundamentally statistical pattern matchers and sophisticated next-word predictors. They are not, by their nature, provably correct logical reasoners.
They're good at plausible text, not necessarily logical truth.
They're prone to what we call hallucination, generating plausible but factually incorrect information. And they are notoriously poor at the kind of rigid, multi-step, symbolic manipulation and ironclad logical deduction required for complex mathematical proof.
They can't guarantee correctness.
They can act as powerful intuition pumps or brilliant assistants, generating ideas or checking steps, but they cannot currently be trusted as autonomous, self-sufficient provers. The burden of ultimate verification still rests firmly with human experts.
Assistants, yes.
Yeah.
Solvers, not yet.
A more realistic and immediate application is to use AI as an invaluable tool for verifying human-generated proofs. As prominent complexity theorists have suggested, a truly rigorous test for any claimed proof of P versus NP would be to run it through a highly sophisticated reasoning AI with the prompt, "Give me a critical review of this paper," rigorously checking every logical step.
Using AI as the ultimate tireless peer reviewer. That makes sense.
An AI could be trained to tirelessly check the logical consistency of a proof, identify subtle flaws, and flag potential errors, serving as an invaluable, tireless assistant to human mathematicians, augmenting their capabilities. Imagine a world where every new mathematical discovery could be instantly, rigorously vetted by an AI.
That alone would accelerate mathematics significantly. Now, what about that speculative future? Could a future AI do it?
Wow.
A truly speculative future would be if P and P is true, in which case one could imagine a highly advanced AI, perhaps a distant successor to AlphaDev, discovering a polynomial time algorithm for an NP-complete problem through a massive directed search. Such a discovery would implicitly prove the equality.
So if P and P, AI might find the proof by finding the algorithm.
Possibly. However, proving P and P is a fundamentally different and far harder challenge. It requires proving a negative, that no efficient algorithm can ever exist for an entire class of problems. This demands a lower bound proof, a type of reasoning that is far more abstract, foundational, and for which current AI search-based approaches are ill-suited.
Proving something can't be done is harder than finding one way it can.
Much harder, mathematically speaking. Misguided attempts to resolve P versus NP by drawing analogies to Gödel's incompleteness theorems or Heisenberg's uncertainty principle highlight the immense difficulty and the incredibly high standard of rigor required for a Millennium Prize problem. Such arguments are based on metaphor and philosophical parallels rather than rigorous mathematical deduction, and they utterly lack the formal mathematical bridge required to resolve such a deep problem.
So no easy philosophical outs, it needs math.
It needs hard math. The current role of AI in the grand challenge of P versus NP is therefore not that of a primary solver, but of a powerful, multifaceted tool. It is an amplifier of human capability, allowing us to probe deeper than ever before.
An amplifier, not a replacement.
On one hand, through machine learning for combinatorial optimization, AI helps us cope with the practical consequences of living in a world we assume is PNP by creating better heuristics and approximate solutions for the incredibly hard problems we face daily in logistics, design, and science.
Helping us live with PNP.
On the other hand, through its integration with formal methods, AI helps us sharpen the very tools of mathematical rigor and logical deduction that would be needed to construct a definitive proof, whichever way it ultimately lands.
And helping us potentially prove PNP or PNP.
Exactly. This creates a fascinating duality where AI is simultaneously helping us manage the problem's practical fallout, while also advancing the formalisms required to one day solve its deepest theoretical mysteries.
So what does this all mean for us? We've journeyed from the universe's most vexing puzzles through the great divide of P and NP, uncovered the Rosetta Stone of NP completeness, and explored AI's multi-pronged assault on these barriers.
It's been quite a trip through complexity land.
It's crucial to distinguish the tangible progress AI is making in finding practical, high-quality approximate solutions to NP-hard problems, acting as a heuristic architect.
Role 1, the apprentice.
And discovering more efficient algorithms for problems already firmly in P, acting as an algorithm discoverer.
Role 2, the alien genius.
Should not be confused with actually resolving the fundamental P versus NP question. The former are truly impressive engineering achievements that are transforming industries. The latter remains a monumental theoretical challenge far beyond current AI's reach.
Engineering progress versus fundamental mathematical proof. Very different things.
Indeed.
We connect this to the bigger picture, the relationship between computational complexity theory and artificial intelligence is becoming deeply symbiotic. Complexity theory provides the essential language and framework for understanding the inherent difficulty of the problems that AI is increasingly being tasked to solve, giving us a roadmap of what's genuinely hard.
It tells AI where the dragons are.
In a sense, yes. In return, AI provides a powerful new set of tools to explore the very boundaries of that theory, to manage its consequences, to discover what lies in unexplored territories of algorithmic efficiency, and to sharpen the logical instruments needed to answer its deepest, most profound questions.
So they feed each other.
Exactly. The future is unlikely to see an AI suddenly solve P versus NP in a eureka moment. Instead, it will witness a continued fascinating co-evolution where our theories of computation guide the development of more powerful AI, and that AI, in turn, helps us peer deeper into the fundamental nature of computation itself.
A coevolution. I like that. This raises an important question for you, our listener, as you reflect on this deep dive. After exploring how AI is learning to play these incredibly complex games, often in ways we never imagined, what do you think? Is the perceived gap between discovering a solution and simply verifying one a fundamental feature of our universe, an inherent speed limit to knowledge and creation?
Is P truly different from MP?
Or is it just waiting for a grand breakthrough, perhaps one an AI helps us uncover that collapses it all into an elegant simplicity? Keep exploring, keep questioning, and maybe, just maybe, you'll be the one to spot that secret, easy path in the grand mountain range of computational complexity.